Hello friends, in this video we are going to see the topic methods for handling deadlock under the subject CS3451 Introduction to Operating Systems. This is Satish Pandian, Assistant Professor, Department of CSE, Government College of Engineering, Bodinaikanur. So there are four methods for handling deadlock. In the previous video we already discussed what is deadlock, how to identify or how to detect deadlock. Here there are four ways for handling deadlock. First one is deadlock prevention, second one is deadlock avoidance, third one is deadlock detection, fourth one is recovery from deadlock. So you will see the first topic, deadlock prevention. Already in the previous video, we discussed that there are four necessary conditions for a deadlock. If all the four are true, then there is a deadlock in the system. Mutual exclusion, hold and wait, no preemption, and circular wait. So here, prevention is nothing but by ensuring that at least one of the necessary conditions cannot hold. That is, we have to prove any one necessary condition is false. If all the four are true, there is a deadlock. Any one is false, then we can prevent the occurrence of a deadlock. How to ensure each condition is false. Okay, so we will discuss the first condition, mutual exclusion condition. This condition must hold for non-shareable resources. Example, printer. So printer can be shared by any number of processes. Okay, but the shareable resources do not require a mutual exclusive access. Thus, cannot involve in deadlock. Example, read-only files. Okay. So here, what they are telling means read-only files can be used by any number of processes because all the processes can going to read the content of the file. So these are called as shareable resources. This doesn't require mutual exclusive access, but these kind of resources like printer, we cannot use printers by all the process at the same time. So this is a non-shareable resource. These type of resources need a mutual exclusion condition. The second condition is a hold and wait condition. We have to ensure this condition is false or doesn't occur in the system. How to provide, actually what is hold and wait? A process is holding one resource and waiting to get additional resources. Here how to ensure this is false means whenever a process requests a resource, it does not hold any other resources. Okay. If this condition is true, automatically that hold and wait condition is false. By ensuring that, we can tell this is a false. Automatically, we can prevent from deadlock. Okay. The third one is no preemption. We have to prove that this is false. So how to prove that if a process is holding some resource and request another resources that cannot be immediately allocated to it, then all the resources currently being held are preempted. Actually, no preempted means we cannot preempt or we cannot take resources from one process. But here, if a process is asking for additional resources, but they are not free currently, so the process currently using some resources now they are preempted. That means they are released as free resources whenever entire set of resources are available for a particular process, then only it will be allocated. So no preemption is false here. Automatically we can prevent from a deadlock. And then the last condition, circular wait, we have to prove this condition is false. Here we have to use increasing order of enumeration. That means we have resources and then resource type R1, R2, R3 like that are resource type, like R1 is the CPU, R2 is the input device, R3 is output device like that. Here total ordering given by a function f is the R2n. So f is a function. Here R is resource type, n is number. For example, like this, f of printer equal to 12. That means we have 12 number of printers. F of disk drive equal to 5. We have 5 disk drives. Here a process can initially request any number of instances of resource type Ri. That is, a process can ask for one CPU. Okay, that is this one. After that, a process can request some other resource type. For example, a process can request for memory units. The condition is the Rj is greater than Ri. That means in increasing order, the number of memory units should be greater than number of available processor. That is the condition. So f of Rj greater than f of Ri. So here Rj is memory unit. Ri is the first requested one. That is a processor. So this count is greater than this counter. Like that only the process can request for resources. This is called increasing order. In this increasing order of enumeration, if the process requires resources, we can avoid circular wait automatically. We can prevent the system from the deadlock. So this is deadlock prevention. The second method for handling deadlock is deadlock avoidance. What is mean by avoidance means by having the information about the maximum number of resources of each type that may be requested for each process. Suppose we have a process, that process requires 2 CPU, 3 memory unit and 4 IO devices. This is the maximum number of things used by that particular process. By having this information, like that, each and every process in advance, they are telling how many resources maximum it requires. By having that information, we can create an algorithm that ensures that this system will never enter a deadlock state. That is called a deadlock avoidance. By having all the details, we can create an algorithm. From that algorithm, we can tell the system will not go for a deadlock state. Okay. Under that, first we are going to see safe state. So safe state means very simple. It is a deadlock free state. There is no deadlock in the safe state. If there is a safe state, then we have a sequence like this. P1, P2 up to Pn. This is called a safe sequence. So here a simple diagram is given. See that the bottom part, it's a safe state. Safe state means there is no deadlock. The remaining part is called the unsafe state. But unsafe state, see that inside a small part is called deadlock state. The meaning is all unsafe state are not a deadlocked state. But if there is a deadlock, it is in unsafe state. That's the conclusion here. And then we have a small algorithm in deadlock avoidance. That's the RAG algorithm, resource allocation graph algorithm. In the previous video, we already discussed what is meant by RAG, resource allocation graph. Here, same thing. Along with the previous resource allocation graph, new edges are added. That is indicated as a dotted arrow mark. They are called climb edges. Normally, the climb edges are from process to resource. The meaning of climb edges, the process going to use this particular resource in future. Okay, so the future resources, future requirement are given as these type of dotted arrow mark. They are called climb edges. Okay, when that particular time comes, the climb edges are converted into request edge like this P2 to R1. It is converted into request edge when the resources be like this. The resources allocated to particular process. Okay. So here, what is the use of this algorithm means the bottom 2 points. If there is no cycle, then the system is in safe state. Safe state, what is the meaning? There is no deadlock state. If cycle found, the system is in unsafe state. Unsafe mean what is the meaning? There is a chance of a deadlock. That's a conclusion from this RAG algorithm. Okay. The next algorithm is Banker's algorithm. So previously we seen RAG algorithm. That RAG algorithm is suitable for the resources with single instance. But here Banker's algorithm is going to be used for the resources with multiple instances. So the Banker's algorithm are going to use several data structures, available, max, allocation, and need. Okay. So before that, why the algorithm is called as Banker's algorithm means the system used here is followed in banks, is followed by banks. So see that the Banker's algorithm, because this algorithm is used in banking system to ensure that the bank never allocates its available cash such that it can no longer satisfy the needs of all customers. Similarly, here the system will not allocate the resources to the all processes until it doesn't satisfy the needs of different process. So that this algorithm is called the Banker's algorithm. So these data structures we are using here, available means currently available number of resources in each type. Maximum is every process tells in advance maximum how many resources are required in each type. Allocation means current allocation. Currently, how many resources in each type are allocated to every process. So from this, we need to find the need matrix. So need is equal to maximum minus allocation. So maximum how much is needed, currently how much is allocated. If we subtract, remaining need is we can get. Okay. So here safety algorithm, under Banker's algorithm. This is used to check whether the system is in safe state or not. Okay, there are n number of processes. We have to take one by one with the condition. What is the condition means here? Need is less than or equal to work. Work is nothing but available. Okay, so process needs should be less than the available or work. In that case, we have to take that process and allocate the needed resources, then make that processes completed. That is finish of is equal to true. Like that, you repeat the previous two steps for all the processes. After after of all execution, finally we have to check the finish of I is equal to true for all I. All I means for every process. Then the system is in safe state. Suppose we have five process, for all the five process, the finish of I is true, then the system is in safe state. Otherwise, it is in unsafe state. Again, we have one more algorithm here. It is called a resource request algorithm. This is nothing but whenever a process requests for additional resources, whether it can be granted or not. For ensuring that we have this algorithm, then additional request is given by this format. Request of I in array symbol j equal to k. The meaning is the request is given by process pi of the resource type Rj. So Rj resource, the J type resource only the process requires. How many number the process wants? K number of instances. That's the meaning. Okay. This algorithm consists of 3 to 4 steps. The first step is the request should be less than need. So need we are calculating already. Previous algorithm is saying no. Need is maximum minus allocation. That is, this is the current need of a process. The new request should be less than the need of that particular process. Then only we can go to next step. Otherwise, we need to generate an error condition. The process exceeds its maximum claim. Suppose the first condition is true, we are coming for second condition. Here, request less than the available. Because the resource not at all available, we cannot allocate it. So the request should be less than or equal to available. Then go to next step. Here we are allocating resources. While allocating, we need to modify these steps. Available equal to available minus requested. We have to subtract the available because we are allocating some amount of resources to the process. So we have to update the available. New resources we are allocating to the process. So allocation is added and then need also subtracted because new need is lesser than the previous one. Okay. If the resulting resource allocation state is safe, then the transaction is completed and the PI is allocated its resources. So if when all are over, again we have to execute a safety algorithm. Okay. If everything is okay, this request can be granted. Okay. So that is deadlock avoidance. So deadlock avoidance, safe state. What is mean by safe state we've seen, and then RAG algorithm, that is mainly all the resources with only one instance. If the resource have multiple instances, we have Banker's algorithm. Under that, a safety algorithm and a resource request algorithm. Okay. And then third technique for handling deadlock is deadlock detection. Simply, it is used to detect deadlock in the system. Here we have two-sided things. When every resource type have single instance, what we have to do? Every resource have multiple instances, what we have to do? Okay. When every resource have single instance, we need to create a graph called wait graph. This graph is constructed from RAG by removing all resources. So see that this is RAG. Here R1, R2, R3, R4, R5 are resources. They need to remove the resources, the resultant graph. This one. This is called a wait for graph. So how it is constructed means, for example, see that a P1 to R1 we have an edge, R1 to P2 we have an edge. So remove this R1, directly we have edge from P1 to P2. That is given here, P1 to P2. Similarly, P4 to R2, R2 to P1. So remove this R2, P4 to P1, we have an edge. So like this, we have to create a new graph. This graph is called a wait for graph. The conclusion is in the wait for graph, there exists if there is a cycle, there exists deadlock in the system. So in the wait for graph, if there is a cycle, the conclusion is there is a deadlock in the system. This is for every resources have single instance. When the resources have multiple instances, we have another algorithm. This is like banker's algorithm. The same type of coding will be there. Okay. So here finally we have n process. We have to check finish of I for all the process. For any particular process, if the value is false, then that process alone is in deadlock state. The final method for handling deadlock is recovery from deadlock. So here, two ways we can recover from a deadlock: process termination and resource preemption. Process termination is just a process in the system. We have 10 process. Among 10, 5 processes involved in deadlock. So here, what we have to do? We have to terminate the process. In the two possibilities, about all deadlocked process. Among totally we have 10 process. Among that, 5 are deadlocked. So we have to abort all 5 deadlocked processes. That is the first option. Second option is we just don't want to abort all deadlocked process. We have to abort one by one. So terminate one deadlocked process at a time, and again check the system whether it is in deadlocked state. If that, again terminate one more process. Like that, one by one we have to terminate. Okay. This is called the process termination technique. And then resource preemption means preemption is nothing but taking or recovering or collecting or acquiring resources from the process. So here resource preemption, we are going to take the resources from the process. From which process we are going to take, that we have to choose. That is called selecting a victim. Selecting a victim is nothing but to choose the process from which we are going to retrieve the resources. Once we retrieve the resources from the process execution will be stopped. So the process is in blocking state. After some time, when deadlock is eliminated or there is no deadlock, again we have to restart the system. So allocate resources to the process. So that case is called a rollback. Rollback is again allocate resources to the process, and the process started to execute from where we stopped. That is called rollback. And then here we have to ensure the starvation. Starvation is waiting time. The waiting time for the process will not be for long time. That should be a limited waiting. That also we need to ensure. This is called a resource preemption. By using these two techniques, we can recover from a deadlock. So these are the 4 methods for handling deadlock: prevention, avoidance, detection, and recovery. Thank you.